Hello everyone, welcome to chapter 26. Now you may have noticed in chapter 25, excuse me while I move around here, trying to get comfortable in my chair. Chapter 25 kind of jumped all over the place because it was trying to be about waves in general. So it talked about pendulum waves, and it talked about water waves and sound waves, and that remember the equation velocity equals frequency times wavelength. Now this equation is going to be really important because it's going to be true for sound, for water, for whatever wave we're talking about. This equation is going to hold true. So keep that equation in mind. Now this chapter is just about sound, and we're going to come back to the Doppler effect, which was introduced in the last chapter, and basically everything about sound. Sound is a form of longitudinal energy that moves through space. Sound requires a medium. It cannot go through a vacuum, but it's just energy transfer. Okay. So what causes sound, like any wave, is a vibration, some sort of a disturbance. And if I have a material object that vibrates, like my vocal cords, it vibrates the air or the medium, and that's what we interpret. We have a sense of sound. We have ears that can interpret that for our brain. Any vibrating object can produce sound in a medium, right? This is just a tuning fork. It's just vibrating in the air, and yet we can hear it. It may not be loud, but we can hear it. In a saxophone, it's the reed. For me, it's my vocal cords. In each case, the original vibration causes something larger or more massive. The vibrating material transmits that energy in a longitudinal wave. So we have sound, and it is a longitudinal wave. Don't forget that. Through a medium. It has to have a medium. Okay. And it's a wave. So it's a wave. That's something that transmits energy. Okay. Now, we've talked before, we have frequency and wavelength, a few extra tidbits for sound. We have a subjective impression of sound, and what we call that is pitch. So when we use the word pitch, basically that means the same thing as frequency. We're just saying that it has a high frequency, right? But we have, since humans don't really hear frequency, we hear pitch, and not every human hears pitch the same way. That's why we use pitch, because frequency is a specific hertz measurement. That's a mechanical measurement that our brain doesn't make. Our brain just makes a subjective interpretation of the frequency, and that's what we call pitch. Now, a normal human can hear, or I shouldn't say normal human, a normal young human can hear frequencies from 20 to 20,000 hertz. And in class, I'll usually play, uh, like you can go to websites and they'll play a sound, and I'll turn the TV up really loud and it actually hurts my ears at some points. And it'll start with 20 hertz and it'll move up. And that's usually about what you can hear. Now, dogs can hear much higher than that. I am older now. I only hear up to about 17,000 hertz now. I've had students claim that they could hear all the way to 21,000 before. But mostly you lose the higher frequency end just because damage to our eardrums over time. Now, remember how we had ultraviolet and infrared? I mentioned infrared was below red and ultraviolet was above blue. And with ultraviolet, the frequency was getting bigger, but the wavelengths were getting smaller, and that was called a blue shift. And we had a red shift, which was when the wavelength was getting longer, but so the wavelength got bigger, frequency got smaller. Well, infra and ultra are also used with sound, but we don't use infrared and ultraviolet. Instead, we use infrasonic, ultrasonic, and it means the same thing. Infra is when the frequency is smaller, and ultra is when the frequency is greater. So dogs, for instance, can hear ultrasonic sounds, some up to 40,000 hertz, which is crazy, and bats up to 100,000 hertz, which is just amazing to me. I think that'd be awesome. Okay, so infrasonic, ultrasonic. Now, what is the source of all sound? It's anything vibrating in a medium. Okay. Now, as the source of a sound vibrates, you get compressions and rarefactions, like I drew in the last chapter, like that. I'm making sound move. I'm compressing the air when I snap together, and that compression moves outward as that smack. The same thing you see here in the spring. Here we have the compressions. We call this a compression. I also have heard it called a condensation. And then out here is called a rarefaction. It's where it is rarer. Think about it that way. It's more rare here, so it's a rarefaction. Now, any type of compression, like opening a door or closing a door, if I move the air in, I compress it. If I move the door out, I rarefact it. So any motion can cause sound, basically. Any disturbance of a medium can cause a sound. And that pulse of sound we call a compression. And the pulse of low pressure is called a rarefaction. Okay? And it's the pulse that moves. So here you see compression, rarefaction, compression, rarefaction. Now consider that as a sound vibrates, one wavelength is from one compression to another compression represents one wavelength. And one wavelength also represents one vibration of this tuning fork. So every time the tuning fork vibrates, it compresses the air. So mechanical energy is what is causing, mechanical vibration is causing the sound vibration. It's a transfer of that mechanical energy through the sound wave. Okay, so how does a sound wave travel? It travels through the medium by vibrating the medium. And the energy of those vibrations, this particle is vibrating and it bounces into this particle. This particle gets the energy and then this particle gets the energy. The particles aren't moving, it's the energy that's moving as they collide with one another. Now sound can travel through any medium, solid, liquids, and gases. It can't travel through a vacuum. And it turns out that most sounds we hear are through the air. But when we hear things through other objects, we can still hear it. Like if you put your ear up to a wall, you can hear the sound vibrating through walls. Now we don't hear it as well because solids and liquids are generally not. We don't hear it the same. I didn't mean to say as well. We don't hear it the same because solids and liquids are compressed. If you are a compressed state of matter, and if sound requires that particles collide with one another in order for the sound to be transmitted, the more tightly packed the particles are, the easier it is for sound to travel. So solids and liquids actually allow for sound to travel better than air. As the closer you get to a vacuum, the worse the sound travels. So in general, sound is transmitted faster in liquids than in gases, and still faster in solids. So solids are the fastest, then liquids, then gases. That's why sticking your ear up to a door can sometimes allow you to hear things. Now, if I put that sound in a vacuum, and I usually try to do this, but I doubt that, with these shorter periods, I doubt I'll be able to do this here, but I'll put somebody's cell phone, I'll put like my cell phone in the vacuum chamber, and I'll turn the vacuum on, and then I'll borrow somebody else's cell phone, and I'll call my cell phone, and as the air gets pumped out of the chamber, you can no longer hear the phone ringing, right? So I'll try and do a vacuum chamber sound. I just make notes to myself to remember other videos that I want to upload for you guys. So what medium transmits sounds? All of them but a vacuum. The speed of sound in a gas depends upon temperature and the type of gas. The bigger the particles, so the bigger the mass of the particles and the higher the temperature of the particles, the easier it is for sound to travel. So the speed of sound in a material depends upon the mass of the particles of the gas and the temperature of the gas. If it's traveling through a material like a solid material, it depends upon the elasticity, how easy it is for those particles to vibrate. What do we want to know here? So lighter particles such as hydrogen and helium move faster and transmit sound faster. Smaller particles transmit sound faster than heavier particles. All right. If you increased elasticity, steel is very elastic. It vibrates very easily. Putty doesn't vibrate easily. Sound does not travel well through putty. Sound travels really well through steel. In fact, it travels 15 times faster through steel than it does through air, and about 4 times faster in water than in air. So water is better than air by about 4-fold, steel by about 15-fold. So the medium, and I've said this before in the last work, medium influences speed. And remember, source influences or determines frequency. And when we had the Doppler effect in the last chapter, so if I do Doppler, source or observer motion alters, and I'm going to call this apparent frequency, because the frequency at the source stays the same. It's just the frequency that the observer hears changes. So these are kind of some good things to keep in mind. So let's talk about the speed of sound. How far away is a storm if you note a 3-second delay between a lightning flash and the sound of thunder? Well, sound moves, the velocity of sound in air is around 343 meters per second at, I think that's 25 degrees Celsius. So if it took 3 seconds, now light moves at 300 million meters per second. So fast that it's basically instantaneous. So if it took that sound 3 seconds to get to me, it would be it'd be 3 times this. What would that be? 1,000 and, so it'd be 1,029 meters away. Now they rounded, they used 3,400 and they rounded it to 1,000, but it's basically a kilometer away. If it takes 3 seconds to hear sound, it's about a kilometer away. If it takes 4.5 to 5 seconds, it's about a mile away. So what determines the speed of sound in a medium? The speed is affected by, I don't have it in the notes here, but elasticity, how elastic, all right? So let's do V of sound. No, metal is faster than in a liquid, is faster than in a gas, but elasticity matters. So if you have like putty, sound doesn't move well through putty. Okay? And that moves us up to sound intensity, but I'm going to save loudness for the next video.